Good afternoon, everyone. My name is Rabarsi Televigo. I'm the one who referred the maximal flow problem. The maximal flow problem is optimization theory. Maximum flow problems involve finding a possible flow through a flow network that obtains the maximum possible flow rate. Objective function of the maximal flow problem. The maximization problems is to determine the maximum amount of the flow following per unit of time from the source S to sink D in given flow network. Example of maximal flow problem. Maximum flow problems involve finding a possible flow through a single source, single sink flow network that maximum. Another example of the maximum problem. In the shortest route problem, we determine the shortest route track from the region Los Angeles to 6 destination. In the minimal spanning tree plan, we found that the shortest connected network for the television cable. In neither of these problems, we are the capacity of branch limited to a specific number of items. However, there are network problems in which the branches of the network have limited flow capacities. The objective of this network is to maximize the total amount of flow from the origin to a destination. These problems refer to maximal flow problems. Maximal flow problems can involve the flow of water, gas, or oil through a network of pipelines, the flow of forum through the paper processing system such as a government agency, the flow of the traffic through a road network, or the flow of the product through a production line system. In each of these examples, the branches of the network have limited and often different flow capacities. Given this condition, the decision maker wants to determine the maximum flow that can be obtained through a system. An example of the maximal flow problem is illustrated by the network of a railway system between Ohama and St. Louis. Shown in figure 7.18, the Scott Tractor Company ships tractor part from Ohama to St. Louis by railroad. However, a contract limited the number of railroad cars and the company can secure on each branch during the week. Just like Ohama is number 1, then the St. Louis is number 6. Given these limiting conditions, the company wants to know the maximum number of railroad cars containing tractor part that can be shipped from Ohama to St. Louis. During the week, the number of railroad cars available to the tractor company on each rail branch is designated from the number 1 branch of the immediate right of each node, which represent the rail junction. For example, 6 cars are available from the node 1. That is 1. 6 cars are available from the node 1. Then Ohamas to need to 8 cars are available from the node 4. And 6 St. Louis are the and so forth. The number on each branches is the immediate left of each nodes is the number of cars available for shipping in the opposite direction. I repeat. For example, if the 6 cars are available from the node 1, Omaha to need to 8 cars are available from the node 2. To node 5, 5 cars are available from the node 4. To need to 6 to St. Louis, and a fourth of the number on each branch is to the immediate left of each nodes is the number of cars available from shipping in the opposite direction. The first step is determining the maximum possible flow of the railroad cars through, and the rail system is choose any path arbitrary from the region destination and ships as much as possible on the path. In the figure 7.19, we always arbitrarily select the path 1 to 5 and 6. The maximum number of railroad cars that can be sent through the route is 4. We are limited to 4 cars because that is a maximum amount available on the branch between nodes 5 and 6. This is path shown in figure 7.19. Noting that remaining capacities of the branches from the node 1 to node 2 and from the node 2 and to node 5 are the 2 and 4 cars respectively, and that no cars are available from the node 5 to node 6. These values were computed by subtracting the flow of 4 cars from the number available. The actual flow of the 4 cars allow each branch is shown enclosed in a box. Notice that the represent input of your 4 cars input node 1 and output of the 4 cars from the node 6 are also designated. To recompute the branch below in the both directions is the final adjustment on this path is to add the designated flow of the 4 cars to the value at the immediate left of the each node on our path 1, 2, 5, 6. These are the flow in the opposite direction. Thus the value of 4 is added to the zeros at the node 2. 5 and 6, it may seem incurious to designated flow in the direction that is not possible. However, it is the means used in the situation solution approach to compute the net for flow in the branch. If for the sample, a lateral iteration shows the flow that occurs from the node 5 and 2, then the net flow in the correct direction will be computed by subtracting this flow of a 1 in the wrong direction from the previous flow of 4 in the correct direction. So, the result will be a net flow of a 3 in the correct direction. We have now completed the iteration of the solution process and must be repeated the preceding step. Again, we arbitrarily select a path. This time, we will select the path 1 on 4, 6. As shown in figure 7.20, the maximum flow along this path is a 4 cars, which is subtracted at the edge of the nodes. This increases the total of flow through the network to the 8 cars because the flow of the 4 along path is 1 and 4 and 6 is added to the flow previously determined in figure 7.19. As a final step, the flow of a 4 cars is added to the flow along the path in the opposite direction is a node 4 and 6. This one. Now, we arbitrarily select another path. This time, we will choose the path 1, 3, and 6. With a maximum possible flow of 6 cars, this flow of a 6 is subtracted from the branch along path 1 and 3 and 6 and added to the branch in the opposite direction as shown in figure 7.21. The flow of the 6 of this path is added to the previous flow of the 8, which result in total flow of 14 railroad cars. In another page, notice that the point of the number of the path we can take is restricted from, for example, we cannot take the branch from the node 3 to node 6 because zero flow capacity is available. Likewise, no path that include the branch of the node 1 to node 4 is possible. Then the available flow capacity along the path 1, 3, and 4 and 6 is a 1 car shown the figure 7.22. In the last that I discussed, this increased total flow from the 14 cars to 15 cars. The resulting network is shown in the figure 7.23. Close observation of the network in figure 7.23 shown that there are no more paths with available flow capacity. All paths of the nodes 3 and 4 and also the 5 shows zero available capacity, which prohibits any further paths through the network. In how we complete the maximal flow solution. For example, problem of the maximal flow is 15 railroad road cars. The flows that will occur along each branch appear in boxes figure 7.23 in the last that I discussed. 1. Summary the step of the maximal flow solution method as the follow. 2 is arbitrarily select any path in the network from the origin to destination. And the 3, adjust the capacities at each node by subtracting the maximal flow for the path selected in the step 1. Add the maximal flow along the path in the opposite direction at each node. And the 4, repeat the steps 1 and 2 and 3 until there's no more path with the available flow capacity. Then step of the maximal flow solution method. Thank you.